Virtual reality applications, such as entertainment and healthcare, rely heavily on high-resolution displays and interactive frame rates. These high computational demands highlight the importance of rendering acceleration. Foveated rendering accelerates rendering by using high-quality rendering for the foveal region and low-quality rendering for the peripheral region. Foveated rendering lowers pixel sampling rate at the periphery to approximate the human visual acuity fall-off model. However, these techniques do not fully leverage binocular vision, as the non-dominant eye has inferior visual acuity compared to the dominant eye. Previous study applies a higher level of foveation to the non-dominant eye than the dominant eye, and shows enhanced acceleration compared with existing foveated rendering methods. However, this single-parameter foveation method creates a gap between the pixel sampling rate and the visual acuity model at the periphery, resulting in unnecessary rendering costs. Thus, better integration of foveated rendering with the dominant eye theory is needed. Our previous work DEEMP introduces distinct sets of foveation parameters tailored separately for the two eyes. For each eye, the visual field is divided into 3 nested layers based on eccentricities. Each layer uses a single parameter to control the level of foveation. DEEMP narrowed the gap between the pixel sampling rate and the visual acuity fall-off model while maintaining perceptual quality. However, the eccentricity range for each layer is fixed. We further argue that the eccentricity ranges should vary between the eyes due to inter-eye, individual, and scene-specific differences. Therefore, in this paper, we propose the dominant eye-aware asymmetric foveated rendering method, namely DEFA. The DEFA allows users to customize eccentricity sets based on their eye's traits, and supports asymmetric configurations between the two eyes. With this approach, the pixel sampling rate remains minimal and approaches the human visual acuity model. Our experiments validate that the optimal eccentricity sets differ between the dominant and non-dominant eyes. Furthermore, the experimental results indicate that eccentricity layer distributions are influenced by scene texture complexity. The deferred shading pipeline has demonstrated a notable reduction in rendering time when compared to other existing methods. Here is the example video. Thanks for your watching.